So today is our final class of Chem 31. Hope you're excited. I guess the end of the tunnel, or the light at the end of the tunnel, is right there, or there's lots of ways you can look at that. Hope it's on a train that's coming. But let me give you a rundown on our options here for what we're going to do for the next few days, because even though it's the final lecture, it's obviously not over yet. So we will have a final next Wednesday, I believe that's the 25th. And it is as scheduled at 12 to 1:50. We will be here. There's an alternate room. I actually don't know what the alternate room is. It's like Christmas. I'm only going to find out on Christmas Eve, which is Tuesday evening, what that's going to be, but I'll make sure that you're ready for that. But it will start here. Okay? So there's no change in the setup of the final exam. It will be here in this lecture room, just the time and date of course is as scheduled, 4:25 from 12 to 1:50. So it's roughly 2 hours. Okay? You have to be out of it by 2 o'clock. We will also do a review session on Saturday. This Saturday, I believe that's the 21st, so 2 days. And it will be 154, that's next door to your right, down the hall, and with 1 to 150. Okay. So that is our final review session. Feel free to bring questions, and I'll go through the material, give you a little bit of a rundown if I don't get enough questions. But the main idea is that you have a chance to ask questions. I will also have my Tuesday office hours. So if you want to stop by on Tuesday, I will do the office hour from, I guess, 1 to 1:50 as usual. There are alternative final options. So previously I couldn't give those to you. Literally I found out about these about 6 p.m. yesterday. Okay. So this is not because I held back information, but because it was very slow to get this all organized. And it's complicated. Okay. So I'll run you through these options. This is a copy from Courseware. So this is already up since last night. I posted it around 9:30 p.m. or so on Courseware. So I hope I got this all right. So the alternative option, well, first of all, this is our regular final. That's as normal. We'll do that. But we do have some extraordinary accommodations. So there's option 2. So you have 3 options. First option is self-explanatory. Second option is same time, different location. In fact, it's a location of your choice. You can go, I believe, to Hawaii. It could be in San Francisco, in Boston, in downtown Philadelphia. All these places, I just throw them out. I have no idea where you actually could be, but in principle, everything's possible. However, what you need to do is contact this 5-letter organization here at Pitt, which has this website. And as you can see here from the link, they're going to give you some information about testing centers. So what is a testing center? A testing center is some kind of construct, a house, and a garage, I don't know, some kind of organization that has a controlled environment where they have usually a computer. They're mostly set up for multiple choice stuff, but they have desks. And they will check you in, check your ID, and then give you the exam, the same exam that people have here. This is all organized by CIDDE. I do not have such an organization, but we have found that this is information that I did get yesterday evening or yesterday late afternoon. So that's why I couldn't tell you about it before. But they do tell me that they can handle this, that unless what they expect you to do is complete the form. Like anything in life, there's a form. I looked at it, it looks long, but it's not impossible to solve that. I think if you can do well in Chem 31, you have a chance to actually fill in that form. And so then they will get back to you. You have to suggest locations, so you have to tell them if you're going to be in Oahu or on the Big Island or somewhere. And then they will see if they have a partner testing center that can contract this out. It all sounds pretty complicated to me, but it is an option for those who have already decided that Oakland is not the place they want to be and have gone far away and so don't want to come back. And we have a few of them. There are not many, but So this is self-explanatory again, I hope, but it is in the hands of CIDE. So you have to understand this is whatever happens, once you submit that form, you negotiate with them. I cannot personally call up the sector and organize this, so you have to negotiate with them. They told us that they have enough personnel that is not on sick leave, that they can actually do this. I made up the deadline. They want you to do this immediately. I made up a deadline on Monday because I think some of them might want to think about this, I don't know. But I don't know if they're on that deadline or not. So if you want to go with that option, then you need to do this as soon as possible. Of course, I'm talking to the wrong crowd here because you guys are obviously still here. And so it's mainly for the people that have already left. But I did, I think, post already for a while that if you want to do the final, you have to be connected to Courseweb. And this is what is now available there. So that's option number 2. There is an option number 3. So since this is out of my control, and I don't like things to be out of my control. I hate having things not under my control. So I have a third option that is under my control, and I have to compromise with those. So we will do a makeup final, and it will be at the beginning of the fall term because I cannot expect people to come back during the summer and do a final year. Okay, that will be unreasonable, and I have to offer it to everybody. It has to be fair. So there will be a third exam, option at least, which will be on the PIP campus. So I think eventually people will have to come back. It's better or for worse in the fall. It will be the first week of the fall term this year. And I will post the time and location on Courseweb again. And so if you don't want to do option number 1, and option number 2 doesn't work out for whatever reason, because maybe it's scary to do the final next week, you have option number 3. And on the other hand, the registrar's office, also something we found out yesterday, does not allow us to use any other grade besides a G grade for those who delay the final until the end of the finals week. So I have to submit grades, and they're not going to take, maybe later or something for an answer. They want a grade that they're familiar with, and so the G grade has to be used. The G grade is inappropriate for the situation. For some reasons that I spelled out here, there are consequences of the G grade. I really do not like giving G grades because half of the G grades end up having issues because people have a hard time fulfilling the requirement. Okay? So you do get a G grade. You have to let me know that you select this grade because it is a bad option. But it is workable if you manage it. It's like with anything, you have to really be aware what the G grade is, which means you have to do this final at the latest here. There's only one option. You have to do this final this week. I will not give a makeup of an alternative final option. That is not fair anymore. Then you'll have to do these things, and it's not in your interest to have that many alternatives and procrastinate on that. So you can procrastinate over summer, having the sword of Damocles in the form of Chem 31 hanging over your head while you're on the beach in Waikiki. But that's okay. Some people can handle that, and then you can come back in the fall and do this exam right in the first week. It will be scheduled on campus. It will be in a room big enough for those who want to take it. But please do send me a confirmation, okay, that you select this option, because when I put in the G grade, there's certain things that are being triggered, which means you have to later on somehow turn that G grade into a letter grade by getting something done that I accept, which is in this case you have to do the final, and there's really only one option for that. So otherwise you cannot graduate. There's also, as I put on in here, this is wording I took from an email from one of our provosts. One of our deans maybe, but it was from the administration, so I didn't make up this complicated wording here, but I did paste that in some of the issues with G grades. Okay, but it is an option, as long as you're sure that you're ready to take the final exam in the first week of the fall term. That's option number 3. In the meantime, you have to let me know that you're going to go with the G grade so that I have a record that you really want a G grade. For those that I don't hear back, I will give them a letter grade at the end of the finals week, because you're still better off having a letter grade than having the G grade that you forget about, I forget about, and then you can't graduate for 2 or 3 years from now. Okay? So there are issues with that. But those are the 3 options. So what do I recommend? Obviously, I don't think I need to say what I recommend, but there are alternatives and they're viable. They just require you to really focus on what you need to do well if you take option number 2 or option number 3. If you take option number 2, you need to get this going, the CIDDE, pick a center, you know, and let's hope that they at that center do their part of the job, that they get the final exam, and they can give it to you, and then they can get the whole thing back to me. That's all in the hands of CIDDE. If you take option number 3, you know, you're not going to remember all that much coming fall, so you'll have to put in some time for studying, going through things again. I will leave the, if there's a number, the number equals or greater than 1 for option number 3, I will leave the videos on the web, I will leave the additional notes, including today's video on the web, and so you'll have access to that material, but you're still going to have to look at it, and again, memory fades. But it might be a good option if you, you know, you're really ready to study and then you take Chem 32. Maybe that's the way you want to do it. I don't know. It's up to you. So it's fine. You're not going to get penalized in any of these options. It will be the same final for option number 2 and number 1, and it will be an equivalent, very, very similar fair final for option number 3. So there's no difference in terms of the expectations. It's fair because everybody will have to fulfill the same guidelines. It's just at either at different locations or at different times. So I'm working here with the time-space continuum. Okay? And so hopefully that will ultimately pan out for everybody. I hope that 3 will offer an option for everybody, knowing that none of the options is, of course, easy, right? You have to study, but that's what the course is about. I do expect you to know the material and you'll get a grade that is proportional to what you're able to demonstrate as knowledge for this course. I will prepare you for Chem 32, because that is my job here. I need to prepare you, not just in terms of knowing what is in these first 13 chapters, but you're ready to go into Chem 32. And I'm confident that if you take any of these 3 options, you will be ready. If you get a good grade, you will be ready for Chem 32. Okay, are there any questions up front? As usual, you guys are an easy crowd. No? Okay. Well, as I said, you know, this is the best I can do working with all the parameters. And I do believe 100% that this accommodates a lot of personal scenarios. Probably not 100%, right? You can never accommodate that. But it also provides a fair option. There's not a small percentage that gets out of this easily or differently or harder in any way. So I think it is a uniform, satisfactory, but certainly not perfect bunch of solutions. Okay, all right. And let's do what we really want to do is talk about alkynes. Okay. And so what we are continuing here is the discussion on alkynes, actually starting and finishing. So chapter 13 ties a lot of things together, but there are a few new concepts. I want to show you how to synthesize alkynes. We have done a little bit of that. We've done the acetylide displacement reaction, but I'll discuss this again, and I'll show you new ways to synthesize alkynes by elimination. We'll also do a couple of different, 4 different reaction types. Hydration using mercury again, hydrogenation using Lindlar catalyst, dissolving metal reductions, reactions with HCl. And then if we have time, I'll entertain you a little bit with the E-diene and antibiotics. Yep?
How would the curve on the final be affected with medical treatment at the same time?
Sorry, I didn't get that. There's something at the same time you're taking?
How would the curve on the final be affected with everyone not taking it at the same time?
There are, option 1 and 2 are simultaneous. So they're grouped together. So whatever curving is going to be done is going to be for options 1 and 2. Option 3, I will look at specifically on case-by-case basis, and it depends how many people will take that. Okay. So right now, what you can be sure about is that option 1 and 2 will be combined, because they are simultaneous. Okay, I was hoping you would ask an alkyne question. Maybe voting for the E-diene antibiotics up front. But we'll hopefully get to that. Anyway, let's look at the synthesis of alkynes. And one nice approach that ties into the previous chapter is from alkenes. And the actual approach is via an elimination approach. so we can take an alkene. Let's take a phenyl alkene. So this is actually styrene. And we do a dibromination. So Br2 by the bromonium ion, that gives us the 1,2-dibromo ethane, in this case, phenyl substituted. Okay, so I generated a dibromide, and in this case, actually, I've oxidized, formally oxidized the alkene, and so we are now at an oxidation level which is equivalent to what I need to introduce a triple bond. In order to do that, I need to do a double elimination of HBr. And for that, I need a pretty strong base. And this base that has proven that it is very capable of affecting this elimination is sodium amide, Na plus, NH2 minus. The nitrogen, of course, is negatively charged here. And with sodium amide, I can start to plug off these HBr molecules. Okay, so let me draw in one hydrogen that I remove here. And that is the terminal hydrogen, terminal bromide here. And so this is an E2 elimination. And I get a bromo alkene. So I'll put that. And we'll talk a little bit about this bromoalkene later when I tell you about some transformation. So keep in mind that this is one way that I can generate a bromoalkene. We'll see another one from the corresponding chloride in a few minutes. But I'm not done here. I need more, because I just have an alkene back, but now I have a bromoalkene. You can see the difference between the starting material and the intermediate. So I take some more of the sodium amide, and I remove another hydrogen. And so I do another E2 elimination. And that gives me my acetylene. So double elimination, relatively straightforward after dibromination. So there's a little bit of a special feature to this elimination because of the fact that I here have synthesized a terminal alkyne, and that terminal alkyne has an acidic hydrogen. And so the pK of that hydrogen is pretty low. It's much lower than that of the base sodium amide. The pK of sodium amide is maybe 40. Here the pK of this hydrogen is about 25. And so this will react with additional base. So I get one more deprotonation, one more acid-base reaction to go here. But in this case, it's not an elimination, it's a simple deprotonation. And so in the reaction, I actually end up with the sodium acetylide. And you can actually use this. So again, in just a few minutes, I'll show you how you can put this intermediate in our reaction to good use. As a consequence of this mechanism, though, we have to note that we need 3 equivalents total of the base. So 2 are used for the elimination reaction, and 1 is used for the deprotonation reaction to give us sodium acetylide here. And the reason is that these acidities are lower than the acidity here. So once we form the acetylene, then it's going to be deprotonated fast, but then another molecule of an intermediate here of the dibromide or of the vinyl bromide will be deprotonated or eliminated. Okay. So it's not something that we can stop because we generate a more acidic starting product than we have in any of the intermediates and starting material. So we just have to drive this to completion by using 3 equivalents of sodium amide. And of course, when we do the workup, we will regenerate and recover the acetylene. So our product is, of course, the protonated species, and so I'm drawing here the yellow reaction, and so this is the aqueous workup. So you just add water or bicarbonate or ammonium chloride here to quench everything, the reaction mixture, and then you generate your final product, which is the protonated terminal phenylacetylene here in this particular example. Okay, any questions regarding this synthesis? It applies the bromination reaction and then elimination, and has this additional acid-base reaction at the end, again due to the acidity of the product that we have generated. Okay, there's another elimination synthesis, and that is from a ketone. And this is related, so we'll discuss this next. So synthesis from a ketone. And this is again by elimination. So it's very, very similar. Okay, so for this example, let me also use a typical ketone, kind of recapitulate some of the named compounds. You'll see these again in Chem 32, so a lot of this is already kind of looking towards Chem 32. This is acetophenone. Also, the more systematic name known as phenylmethylketone, right? And so we need to convert this to a compound now that we can eliminate. And the easiest way to do that is to use a strong chlorinating agent, PCl5. Remember, PCl5 is one of the reagents we use to generate a chloride from the corresponding alcohol. You can treat an alcohol with PCl5, you end up with a chloride through the mechanism for that at the time. So when you treat this with PCl5, very similar to the mechanism that we showed for the chlorination of alcohols, we get this dichloride. So this is now the so-called geminal dichloride. Because both chlorines sit at the same carbon, the forming carbonyl carbon. And so now you might guess what we're doing is exactly the same we did on the left side here. We now have dichloride, and we treat it with our sodium amide base. So we shovel that into the reaction mixture, and that leads to elimination. First one being just elimination of HCl. Again, we generate a vinyl chloride. Again, make note that this is something that is going to be useful as a starting material later on. We'll see that we can use this if we stop the reaction here. If we use more sodium amide, then we'll get the next elimination. And that will give us again the same acetylene with the same issue that we have in terminal hydrogen. So we have to use one equivalent of sodium amide just to take care of that, because that will occur as an acid-base reaction. And so we'll generate this system, and again, in the conversion to our desired product, all we have to do is add an acid, and so I'm adding here ammonium chloride in the workup as a mild acid to protonate our acetylene. So this is an ammonium chloride workup. So there's some alternatives here. Of course, we don't just, we have other possibilities for doing this with other types of ketones. And so another example that I can show you would be to have, let's say, the T-butyl ethyl ketone. And if we treat this with sodium amine, the second step, first, of course, we again treated with PCl5 in the first step to generate the dichloride. Then we would generate a substituted acetylene, in this case, a methylated acetylene. And when we keep account of our sodium amines here, we can say that for this reaction, we again need 3 equivalents of sodium amine total, if you count them, because of the deprotonation. And in this case here, we would actually need 2 equivalents, because there's a methyl group, and so there's no acidic hydrogen, so we will not have the final deprotonation step occurring, so we only need 2 for the elimination of the intermediate dichloro compound. We eliminate HCl5. So that's just an example that shows you that in fact it does depend on the substitution pattern, exactly how many equivalents of sodium amide will be used up in the conversion. Okay. Any questions regarding the use of ketones as precursors? Yeah. Yes, there still is. You still do that, and the reason is that you have ammonia in there and other things. In order to remove that and extract the organic product into the organic layer, and then the sodium chloride that is being formed, you extract that with the ammonium into the aqueous layer. You still add water. You generally do that because there's salt formation. There might be some side products that are water soluble, and there's also going to be ammonia. So they're inorganic salts, and you remove them by partitioning between organic and an aqueous layer. Okay, so good question about in general what kind of workup is necessary. I don't stress that a lot because it is a very practical aspect. But in general, if there's a workup that's different from an aqueous workup, I will put it down. If it's an aqueous workup, it's kind of implied that you use it. So the direct answer is, in most cases, you can assume that it's an aqueous workup, but it doesn't hurt if you write it down. Now, in some special cases, as we will see, it actually depends. You get a different product, and then, of course, specifically, I will write it down. So the majority of cases, if it's just an aqueous workup, you really don't need to put it down. It's kind of implied in the practical way that you do the experiment. Okay, any other questions? Okay, so let's look at another way to synthesize alkynes, and this is via displacement reactions. And that takes advantage of these intermediates. For example, this intermediate here. So let's say that we go back to this reaction using styrene. And in the first step, I do a dibromination, and that would be an aqueous workup. We would extract the compound into an organic layer, so that's implied, so I don't write it down. And then I would treat this with 3 equivalents of sodium amine. And now I use a different workup, and so I now have to write this down. So I can do this as a separate step, even though it's a workup. for example, I can add methyl iodide. And very often, in order to exemplify that this is something that's done in place of a workup, people will also use this semicolon and then add the methyl iodide at this position. So I'm going to put this in parentheses because essentially this part here kind of shows the equivalent workup. So this goes very nicely into the past question, the question we just had, about the workup. So if there's something special in it, you might illustrate that by, in this case, a semicolon methyl iodide, kind of implying that you're doing an addition of methyl iodide rather than water. But if it's not written there, if nothing's written there, it's usually an aqueous workup. So you can leave out the aqueous workup, that's kind of implied. But if you want to do something else, you have to illustrate that. And more often than not, rather than giving 3 at the third step, because that would imply maybe there's an aqueous workup here, you put it in a semicolon into the reaction in the second step here. So the 3 equivalents of sodium amide, semicolon, then you have methyl iodide adding after the first reaction is completed. So essentially this tells us we do this, we wait for the reaction to be completed, and then we add a bunch of methyl iodide. And so then what you get is a trapping reaction. So remember, if we have this now, the sodium acetylide, and there's no water, and we have methyl iodide, there will be an SN2 reaction. And so the product of this is the methylphenyl acetylene here. So the methylated product. And of course, the methyl group comes from our addition of methyl iodide via the SN2 reaction. So I can write here that this species can do SN2. It does so very nicely because it is a very powerful nucleophile. It's also sterically very accessible because of the the narrow geometry of the alkyne triple bond. So it doesn't take much space. I do have a picture for that to illustrate this. And you can see here on our projection, I have a little graph here for acetylene. See, it's very linear, gain 1.2 angstrom the bond distance here, 180 degrees due to the sp hybridization that's again shown here, just as a flashback to the beginning of this chapter. And then here is a steric model. It also has electronic color coding in there, so the red color illustrates lots of electrons around the triple bond, and then you can see how small this is. The geometry here. This is a beautiful Easter egg. Or maybe a football, depending on what you're more interested in. But it's very, very compact. And so if you protonate here, whatever is here is far away from the site of decoordination, and this is a nice projectile that can come into an SN2 reaction. Yeah?
I noticed that you use a lot of the hex
Phenyl groups, yeah?
Yeah. If you were just use for the synthesis of fine specific reaction, if you were just use propene, would it react?
Same way, yeah. It could be an ethyl, propyl, methyl substituent. For all of these reactions, it would react very similarly. Yeah. So there's no direct influence of what I put down as a phenyl. I just sometimes use cyclohexyl, sometimes use methyl groups or so. So I kind of vary the substituent, but it is not specific for one particular type of substituent. So it could be an R group, and so sometimes I also just use an R substituent to get illustrated as general as well. Okay, any other questions? Yes. Right, over there, the bromination. And the question was, do I have to? No, that's a relatively fast reaction. So So very often the bromination occurs at room temperature and it's exothermic, so you actually have to cool it. So this reaction I would probably do at 0 degrees by dropwise addition of a solution of Br2. So the conditions here are actually relatively mild. So in general, you would do this at lower temperature, also to trap the heat so it doesn't boil off, it doesn't get too exothermic. Yeah. So there's no light and there's no heat involved in the bromination. Okay, so that's a substitution reaction. Again, keep in mind that what we're using here is the intermediate we get in this reaction, which I highlighted here, as well as up here. So we could do the same thing from this intermediate here. And of course, we can use different kinds of trapping agents. Methyl iodide is just one example. You could use other halides, bromides, cyclohexyl bromide, ethyl bromide, that would add those substituents at the other side. We have the terminus of the alkyne, and so we now have an internal alkyne. Previously, we generated these terminal alkynes, where the alkyne is at the end of an alkyl chain or a chain, and here now it's inside the alkyl chain, so it's called an internal alkyne, just as a generic name. So that's one way we can do a displacement reaction. We can also go back and look at other possibilities for doing a very similar reaction. So again, let's actually use here a slightly different acetylene. This is 1-hexyne. And 1-hexyne has a terminal acetylene, which means there's this hydrogen attached here, and we can also deprotonate that. So I can take a strong base, for example, I can use pure lithium and deprotonate the acetylene selectively here, because that's the most acidic hydrogen. And so I generate an intermediate. That's a lithium salt, and of course, I generate butane. And this is not isolated, so we usually do this in a solvent such as THF, tetrahydrofuran. Okay, so we keep this in solution, and then add our electrophile. And so here, let me add a couple of examples of electrophiles. We can add, for example, why don't we add bromobutane. This is bromobutane. And that will give us a product where we have generated a symmetrical alkyne with 4 carbons here on the left side and 4 carbons on the other side. And so we generated a nicely symmetrical system here. We could also add a ketone, like cyclohexanone, and that would do a 1,2 addition. In addition to the carbonyl group. After workup, we would generate a product that has a tertiary alcohol. And this, of course, goes back to our Grignard chapter, the organometallics. And you add a ketone and an organometallic nucleophile, a Grignard reagent, you generate a tertiary alcohol. And so in this case, the organometallic agent is our lithium acetylide. And so I can also do this very generically by saying that I'm going to use an electrophile, and if I do so, the electrophile ends up at the terminus attached to the triple bond from this intermediate. So this is a little bit simpler. If you use an acetylene, a terminal acetylene as a starting material, just use a base. And so then we add in the second step, we add our electrophiles. So it could be an alkylating agent, like a bromide, a chloride, an iodide. It can be a carbonyl compound, an aldehyde or a ketone, or it can be any kind of electrophile that we use in generic fashion to extend the sp2 carbon into a new bond. Yep?
If you added it to the ester, would you get that same like double substitution amount?
Yeah. So if you add it to an ester, very good question, you get the same as we had in the organometallics chapter, you get double addition, and so you end up with a tertiary alcohol with two identical substituents. In this case, the two identical substituents are our triple bonds, our hexyne substituents. Okay, any other questions? So this ties in again very nicely into that chapter. So I think you start to see a little bit how all these chapters come together. So that's the reason why I think it's really important to realize that Chem 31 is a starting point for Chem 32, where you'll learn more reactions, and that's why it's so important to kind of see the similarities between different transformations, because you'll see when you go into Chem 32, you'll see a lot of things coming back, and if you remember what happened in Chem 31, you can connect it to that knowledge. It will be much easier to extrapolate from there. So you don't have to learn new pathways and new transformations all the time. Just kind of add on to the diversity of a transformation by adding more examples. Okay, ready for reactions? Or any questions here for the synthesis of alkynes? If not, then we can do some reactions. Finally, some reactions. These are reactions, of course, to some applications of alkynes. Okay, let's look at the mercury catalyzed hydration. And mercury is at the oxidation level 2, and these are catalyzed hydration reactions. Okay. And so let's actually use one of the alkynes we made here. So we make this beautiful squiggle with a triple bond in the middle. And now we want to make a ketone. So we do a mercury catalyzed hydration. We can use mercury chloride in water. And again, you only need catalytic amounts. So 5 mol% or so is enough. And when we do so, we end up with a ketone. This is our ketone product. And this is an interesting ketone because it's an butyl pentyl ketone. It's not symmetrical anymore. So this is actually decanone, and so 1, 2, 3, 4, 5. This is 5 decanone. Also, what I was actually starting to write was the butyl pentyl ketone, 5 substituents. But the systematic, the IUPAC name is 5 decanone. There are 10 carbons here, and the carbonyl group is at carbon number 5. Okay, so how does this work? Well, it's pretty straightforward, maybe. So I'm getting our mercurinium ion. Okay, so remember the mercurinium ion. and that is being attacked by water. It's a little bit nicer. This is our first intermediate, and then we reshuffle the protons. So there's a couple of steps here, just doing the proton balance, and I skip a little bit of that. And then this is an equilibrium that gives us the ketone. And so what we encounter here is the enol as an intermediate. And so this is actually a mechanism where you really don't need to know the details yet, because this covers some of the subject that will come up in Chem 32. And so you don't need to know about this keto-enol equilibrium yet, but it will be one of the early chapters that will be discussed. So for now, all you need to know here for Chem 31, for our purposes, is that in fact on the mercury catalysis, you can essentially convert the triple bond to the corresponding ketone. So that's all that's necessary. So I put you down a couple of the highlights, particularly to point out that you already know the mercurinium ion and then the attack on the mercurinium ion. But this step and this step will be something that in detail you can discuss, and we will discuss in Chem 32. So I'm postponing this and taking that for your Chem 32 class. So you don't need to know the specifics of this later part of the process yet. Any questions regarding the hydration of the triple bond? Yep.
Did you have some sort of substituent that was maybe like 1 or 2 carbons?
You get a mixture. So there's a reason, of course, I chose a symmetrical alkyne, because that only gives us one ketone product. It doesn't matter what carbon you attack, it's the same product. But if the substituents were different, by having a substituent on one chain and on the other, you'd actually get a mixture. So it is not a regioselective reaction. So the reaction is not regioselective. If you have an unsymmetrically substituted alkyne, you end up with a mixture. So that's a name. It's a special feature of this reaction, which there are solutions to that, but we won't discuss this in the context of this lecture. So we'll just essentially look at symmetrical compound. If it's not symmetrical, there are two products, different products that you will be getting roughly 1 to 1. Good question. Okay, any other questions? All right, and so let's now look at the couple of highlights of chapter 13, and that's the hydrogenation reaction. So just before I leave the mercury catalyzed hydration, let me also give you another point of reflections to the past chapter, chapter 12, where we discussed the oxymercuration reaction. Remember, the oxymercuration reaction of alkenes, so double bonds, requires stoichiometric mercury salts. Okay. And you have a mercury intermediate that I warned you about, right? Don't isolate it, don't eat it, don't inject it, things like that. In this case, it looks like you have an intermediate, but actually you cannot isolate this intermediate. It converts very readily to the ketone, and the reaction uses catalytic mercury salts. So that's a subtlety that I just want to point out so you're not confused. So there's no error here. This reaction is catalytic. This triple bonds is catalytic in mercury. With double bonds, you you get, of course, an alcohol. You don't get a ketone, you get the alcohol, and it is stoichiometric in mercury, and you need a reducing agent such as sodium borohydride for the workup. That's not necessary for this type of reaction. Okay? So the reaction looks similar to deoxymercuration, but it's actually mechanistically distinctly different with distinct different features just in terms of the mercury, but also the type of subsequent reaction and the isolated intermediate that we have. Again, there's some subtleties, some of which are a little bit more difficult to understand for the second reaction here, because we would start to cover parts of Chem 32, and I don't want to do that yet. But if you do have a question on Saturday, I can give you the gory details of this mechanism and explain a lot more on that. So if you want to know more, as always, you just ask a question, and then you can unleash me on this reaction as well. But let's do that on Saturday, not today. Okay, hydrogenations. And we're going to look at two hydrogenations. The first one is a hydrogenation where, okay, let's take this. Okay. This is a pentyne, a 2-pentyne. The triple bond is in the middle here, so this is 2-pentyne. And so we use this and we hydrogenate it. And what we're doing is we're using our hydrogenation system, palladium and carbon, so heterogeneous catalytic hydrogenation in the presence of dihydrogen and solvents such as methanol. And if I do that, I end up with an extremely boring product. Just pentane. Boring because there are no functional groups. And so we have saturated the triple bond. The double bond is an intermediate, but it also gets hydrogenated. So this goes via the double bond. Again, this is our hydrogen addition here, but this is further hydrogenated. And this is fast. So this is an example of the catalytic heterogeneous hydrogenation, because our catalyst is a solid, it's not in solution. And again, the mechanism we discussed in the alkene chapter. The reaction does not stop, it goes all the way to the alkane, in this case, pentane. So if that's what you want, that's okay, but usually it takes a while to synthesize this, so very often that's not what you want. But it depends on the case by case. Obviously, it's not so interesting for pentyne, that's probably not what you want, but if you have a more complicated system, in fact, this can be useful. So I shouldn't make too much fun of this reaction because it can be synthetically quite useful in a longer reaction sequence. So if you put together more complicated compounds, the hydrogenation of the alkyne to the alkane can be exactly what you want. It's a reaction that works very well, but you cannot stop it at the alkene because the alkene is hydrogenated more quickly than the alkyne. So what about if you want to stop it? If you want to stop at the alkyne, at the alkene? You can use a different catalyst, the so-called Lindlar catalyst. And in fact, you don't just get the alkene, you get the Z alkene specifically. So you have a good way to generate a Z alkene from an alkyne. What is Lindlar? Lindlar catalyst has been invented by Mr. Lindlar, and he decided that he wanted to poison something, and wisely he chose an heterogeneous catalyst. So he took palladium, very often palladium on carbon, or more often actually palladium on a different carrier, barium sulfate. But you can do this on carbon as well. So I'm going to put down here in parentheses carbon as well. You can poison palladium on carbon. Barium sulfate is just a heterogeneous salt, an inorganic salt here with a high surface area, so you distribute your palladium over a bigger area. So you can do palladium on barium sulfate, palladium. And then he adds poisons. Okay. So by itself, this is a perfectly functional catalyst, but then you start poisoning your catalyst. And you add lead. Lead is always good, right? Lead is a poison. So lead tetraacetate is not only poisonous for humans, it's also poisonous for catalysts. So it decreases the reactivity of the catalyst. So that's what you want. You want a less reactive catalyst. If you just do the lead tetraacetate and the palladium barium sulfate, you get a catalyst that sometimes is sufficient to stop the reduction, sometimes not. So in order to be completely sure that you can poison something, you use two poisons. And so he used another poison, in this case an organic compound, and this is a heterocycle known as quinoline. And you don't need to know the name yet. There will be a heterocyclic chapter in Chem 32, and you'll see quinoline mentioned in that chapter if you go forward in the full hard book. But that's the other poison. So these are the poisons here. And together they make up the Lindlar catalysts. So these are our additives that decrease reactivity. And together this is a so-called poisoned palladium catalyst. Because it's not as active anymore. So it looks like you have done something to poison it. And so we can now formulate our reaction. Using the Lindlar catalyst, and that allows us to stop at the C alkene acid already mentioned here in the title. Okay, so let's use our 2-pentyne, and in this case we use Lindlar. So this is a very defined catalyst. It's actually trademarked. At one point at least it was trademarked, Lindlar. You can buy it as that poison mixture, and of course you still need